At over 172 astronomical units from Earth, Voyager 1 is completely outside the heliosphere, drifting through the dark, starless vacuum of interstellar space. To send data back across that void, the probe relies on a transmitter running on roughly 22 watts of power. That is less electricity than you need to light a standard bulb in your hallway. Picking up a signal that faint requires massive infrastructure on the ground, like this 70-meter receiving dish at the Canberra Deep Space Communication Complex, combined with the unforgiving mathematics of error-corrected coding to pull data out of the background noise. The survival of this connection relies entirely on a sequence of desperate, carefully calculated maneuvers to stretch 50-year-old engineering to its absolute physical limit. At launch in 1977, Voyager's power system produced 470 watts, but decaying plutonium-238 acts as an inescapable tax, draining roughly 4 watts every single year. After 49 years, available power sits at 220 watts, less than half the original figure. That deficit caused a serious problem on February 27, 2026. A roll maneuver caused power readings to drop so close to zero that the spacecraft nearly triggered its automatic undervoltage protection, a system that abruptly shuts down components on its own terms to save the probe. Operating Voyager is a strict accounting exercise. Every single watt dictates whether the probe stays alive or falls permanently silent. To prevent the spacecraft from shutting itself down, engineers at NASA's Jet Propulsion Laboratory intervened on April 17th, sending commands to switch off the low-energy charged particles experiment. That specific instrument measured ions, electrons, and cosmic rays. Turning it off means sacrificing a stream of data from a region of space where no other human-made craft has ever been. But as this bar chart illustrates, that scientific cost was traded for physical survival. By zeroing out the power consumption of the charged particle experiment, the team reclaimed enough wattage to buy the mission roughly 1 more year of operating headroom. They didn't cut it off completely, though. Engineers left a tiny 0.5-watt sliver of power active. That half-watt keeps a small motor running to rotate the sensor head, preserving a thin chance of reviving the instrument if power somehow becomes available later. The team is performing remote triage. They are constantly forced to weigh the value of deep space science against the raw physical requirements needed to keep the probe alive. Because the 4-watt per year decay never stops, sacrificing one instrument only pushes the timeline back by a few months. To outrun the next deficit, JPL devised a long-term strategy informally named the Big Bang. The plan involves swapping several powered components at the exact same time, trading older systems for lower power alternatives that still generate enough internal heat to keep the electronics from freezing. Swapping foundational systems while the spacecraft is actively running is an extremely delicate balancing act. To manage the risk, they plan to test the procedure first on Voyager 2 in May and June of 2026, since that probe is closer to Earth and has slightly more power. If the test on Voyager 2 succeeds, the engineers will attempt the same maneuver on Voyager 1 in July. The most complex operations in the space program now involve threading exact, high-stakes software commands to fading computers built half a century ago. If the Big Bang maneuver works, the resulting power savings could keep the 2 remaining science instruments, the magnetometer and the plasma wave subsystem, running into the 2030s. Looking at this map, we can see the scale of the next immediate milestone. In November 2026, Voyager 1 will cross a distance boundary of exactly 1 light day away from Earth. The hardware completing that journey looks incredibly analog by today's standards. This is the Voyager spacecraft wrapped in foil during assembly in the cleanroom. A machine built in the 1970s for a 4-year flyby of Jupiter and Saturn is defining the absolute edge of human reach, 5 decades later. Even with perfectly executed triage, the math always wins in the end. At some point in the next decade, the power will drop too low, and the final science instruments will be forced dark. From there, the remaining watts from the dying generators will supply just enough electricity to beam back basic engineering telemetry, likely lasting until around 2036. Teams working in highly advanced modern control rooms on Earth will monitor the diminishing heartbeat of a freezing machine located billions of miles away. Voyager 1's final legacy is the sheer willpower of the engineers managing it. They are fighting an unwinnable war of attrition, stretching every fraction of a watt to keep humanity's eyes open in the dark for as long as mathematically possible.